Can you hear me now?
Yes.
Awesome, thank you. Okay, so hold on, something's wrong. Can you still hear me? Type in the live chat if you can. Okay, awesome. All right, so let's go back a little bit. And I'll have to fix this all in editing later. Okay, so take two. Howdy. Today I'm going to talk about similarity. So, what I want to do is before I get to that, I want to kind of go back a little bit and I want to look at an idea that we were discussing towards the end of last class. Namely, looking at a linear transformation with respect to bases. So here's the situation. We have an ordered basis, u1 through un for Rn, and an ordered basis b1 through bm through Rm. We have a linear transformation from Rn to Rm. And what we'd like to find is a linear transformation A representing L with respect to E and F. So here's what we can do. We can actually figure out what this matrix should be by doing this computation. And here B is the matrix that's basically built from the basis vectors of Rm, represented with respect to the standard basis. So to understand why this works, let's think about it. Well, if we feed our uj to L, we can try to express this in terms of the standard basis. And if we do that, then we'll get here A J1 times B1 plus A J2 times B2 plus blah 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 A Jm times Bm. Wait, I may have messed this up slightly. Sorry, I wanted my indices to be reversed for a reason. So this should be A1j, 2j, and mj. So this is what happens if we try to express uj with respect to, or L of uj with respect to the basis b1 through bm. And here we learn the following fact. The components of the matrix A are exactly the Aij. But the question is, how do you find these Aij? Well, what you can do is you can recognize the right-hand side of this equation as the matrix B times the jth column of A. So if you want to solve for the jth column of A, all you have to do is take this equation and multiply through by B inverse. And it implies immediately that AJ is equal to B inverse times L of UJ. And so this gives us a kind of systematic way to express the matrix of a linear transformation with respect to two different ordered bases, one on the domain and one on the target. Let's do one example. Suppose we take the standard basis. So the standard basis for R2 is 1, 0 and 0, 1. And I'll call this E. Then I'm going to look at a linear transformation, L, from R2 to R2. And then with the basis E, on domain and codomain, so both the domain and the range, the transformation L has matrix A equal to 1, 2, and then here I'll have 1, 1. Now, suppose F is another ordered basis. So say it's the ordered basis. Maybe, how about 2, 3, and 3, 5. So here's the question. Find the matrix representing L from the basis E to the basis F. So here is how we go about doing this. Well, what we want to do is we want to compute L of 1, 0. We also want to compute L of 0, 1. And then we want to express both of these in terms of the basis F. So here we're going to have A1, 1 times 2, 3 plus A1, 2, or I'm sorry, actually A2, 1 times 3, 5. And then here we're going to have A1, 2, 2, 3 plus A2, 2, 3, 5. And we want to figure out what these components are. And if we can figure out what these components are, we'll get the components of our new matrix, A prime. And in fact, just to indicate that these are the components of a new matrix, A prime, I'm just going to give them all primes. So, in order to do this, we can follow the technique of theorem 4.23, which is we compute B inverse. So here, B is the matrix obtained by taking the first column as 2, 3, and the second column as 3, 5. So we want to figure out what this matrix is, or we want to figure out what its inverse is, I mean. So to do that, well, we can apply the following trick, which is, first off, we could switch 5 with 2. And I believe we put a negative here and a negative here. Now let me see if that does the thing. Does this compute the inverse? Yes, it does. So this gives us B inverse. Of course, we could have computed B inverse using row reduction, but I want to save at least a little bit of time today. So now that we have B inverse, what we can do is we can multiply both sides of these equations to figure out what these coefficients should be. Because L of 1, 0 is, because the matrix L is represented with respect to this basis by this matrix, it's going to be 1, 1. And L of 0, 1 is going to be, or 1, 2, rather. What I have to do is I have to multiply this vector and this vector by B inverse. So I'll do that in another slide. So I take 1, 1, and I multiply it through by 5, negative 3, negative 3, 2. If I do that, what I get is 2 and negative 1. I also have to multiply the vector 1, 2 by B inverse. So 5, negative 3, negative 3, 2. If I do that, I get negative 1. And down the second component, I get positive 1. So I have this vector and this vector. Well, according to the previous theorem, what I just did is I figured out exactly what A11, A21, A12, and A22 are. Because this right here is A11 prime and A21 prime. This right here is A12 prime and A22 prime. So this gives me my matrix A prime. 2, negative 1, and negative 1, 1. So what I've done is I've taken my matrix, I've taken my linear transformation, which I've originally expressed in terms of the basis E, and re-expressed it as a linear transformation, or a matrix, from the basis E to the basis F. So that's the power of theorem 4.23. Now, suppose I have a linear transformation L from Rn to Rn and two bases. E and F. So E1 through En and F, F1 through Fn. Well, if we use the basis E, on the domain and codomain. We can represent L by a matrix A, but likewise, if we use the basis B, or I'm sorry, the basis F on the domain and codomain, we can represent L by a matrix B. So we have a linear transformation and we have two bases. We can represent our linear transformation L in terms of one basis. And we're using that basis on both the domain and codomain, so here and here. And if we do that, we can associate L with a matrix A. If we use our other basis instead, our basis F, then our linear transformation will determine a second matrix B in terms of the basis F. And so the fundamental question that we now want to ask is, what is the relationship between A and B? So I'm going to work this out in a special case, and then I'm going to do it in general. Here's our special case. I'm going to let E be the standard basis for R2. So it's going to be 1, 0, 0, 1. And then L is going to be a linear transformation from R2 to R2. And with respect to E, L has the matrix let's see, 1, 2, 1, 1. Now I'm going to introduce a second basis. My second basis is going to be F, and this is going to be 1, 1, and 1, actually, how about this? How about I do -1? And what I want to do is, with respect to F, L has a matrix B. Find it. So, this is our problem. Let's think about how we can do this. Well, suppose we think of our linear transformation from R2 to R2 in terms of the following diagram. Here, I'm thinking of R2 with the standard basis, so I'm going to denote it by a subscript. And with respect to the standard basis, L is represented by the matrix 1, 1, 2, 1. Now, I also want to think of what L looks like with respect to the basis F. So I'm going to draw another copy of this diagram, except the subscript here is going to be F. And my unknown matrix B is going to be here. Well, I might try to figure out what the relationship between B and this matrix has to be. One way to do that is to consider the associated change of basis problem. So I can try to change from the basis E to the basis F. If I do that, then I have change of basis map going down like this. So this is base change map E to F. We'll call it S. And I also have another base change map. E to F on the other side, and in fact it's given by the same exact map. So the linear transformation should be independent of the basis we use to compute it with, which means if we computed our linear transformation by going over like this, it should be the same thing as going down here, and then going over here, and then going up here. We should get the same result. So consequently, what this tells us is that there should be a very tight relationship between B and this matrix. Namely this. B should be equal to the composition of this matrix, 1, 2, 1, 1, with the following. Well, first I start here and I go up. Let me choose a different color for it. So I go up by S, which means I'm taking S inverse. And then I go over by this. So I apply this matrix. And then after, I go down by S. And so I get this relationship between the matrix B and the matrix that we were given. And the only unknown quantity that I have to solve for to figure out B is I have to figure out what S is, the base change map. So let's do that. So let's take both of my bases and let's try to figure out what the base change map should be. So what I want to do is I want to figure out how I go from this basis to this basis. So what does that mean? It means I want to take 1, 0, and I want to express it in terms of these two vectors. So I want to say, okay, this is S 1, 1 times 1, 1 plus S 1, 2 times this. And I also want to express 0, 1 in terms of these vectors. So this is S2, 1, 1, 1 plus S2, 2 times 1, negative 1. And if I know what these S's are, then this is going to tell me what my base change map is from R2 with the basis E to R2 with the basis F. So here's how I can do this. I can make the following observations. This S1 and S12 can be reconceived of in terms of the following matrix equation. In fact, I just want to slightly change my indices and reorder them so it looks better. So here I'm going to have 2, 1 here and 1, 2 here. If I do that, then I can reinterpret the first of these equations as S11, S21 being multiplied by the following matrix. Here I'll have a 1, a negative 1, and a 1, 1, and this is equal to 1, 0. Likewise over here I have 0, 1 is equal to S12, S22 times the matrix 1, 1, 1, negative 1. So if I want to figure out what S11, S21, S12, and S22 are, the first thing I should try to do is I should try to invert this matrix. So what I'll do is I will set, for now, X to be this matrix, and I will compute its inverse. X inverse here is going to be the matrix. Let's see. I can flip the signs of this. Actually, I just interchange these, this and this, and I flip the signs of these. And then I believe I have to divide by the determinant, which is, in this case, negative 2. So I put a 1 over negative 2 on the outside. Let me just check if this works. So let's go over here. I would have the matrix 1/2, 1/2 here, 1/2 here, negative 1/2 here. If I multiply this by this, that works. This by this, I get 0. This by this, I get 1. Yep, I did my calculation correct. So now I can use the matrix X inverse I just found to figure out what these components have to be. So going over to another slide, I find that S11, S21 is equal to 1/2, 1/2, 1/2, negative 1/2, all multiplied by 1, 0. And so this precisely is 1/2, 1/2. And likewise, I find that S12, S22 is the same thing as this matrix. Multiplied by the vector 0, 1. And so this right here will be 1/2 and negative 1/2. And lo and behold, I found my desired matrix S. And S here just turns out to be equal to X inverse, which is the same thing as 1/2, 1/2, 1/2, and negative 1/2. Now that I've found S, I can go back and I can look at my original problem. I was trying to re-express this linear transformation with this matrix with respect to the standard basis in terms of the basis F. And now I know how to switch from the basis E to the basis F. that switching happens via the matrix S. So I can use this knowledge to figure out what B has to be. Because I have to have B is equal to 1 to 1, and then multiplied by S inverse on the right and S on the left. So this will be the same thing as 1/2, 1/2, 1/2, negative 1/2, 1, 2, 1, 1, and then 1, 1, 1, negative 1. And here I'm using the fact that S inverse is the same as the inverse of X inverse, which is just X, which we know to be this. So my calculation of B is simply reduced to multiplying these three matrices. So let's do it. We go to a new slide. And we do the final step in the computation. So this will be the same thing as 1/2, 1/2, 1/2, negative 1/2, and then multiply by the product of this and this. So 3 here, 2 here, negative 1 here, 0 here. And then if I multiply this with this, I'm going to get 5/2 here, and then 1/2 here, and then negative 1/2 here, negative 1/2 here. And so finally, I have succeeded in finding B. And so B here, the representation of the linear transformation with respect to F is simply the matrix 5/2, negative 1/2, 1/2, and negative 1/2. So this is our first example of a change of basis problem. Now, let's articulate what we just did in generality to kind of see how this argument generalizes. So, suppose L is a linear transformation from Rn to Rn with matrix A with respect to a basis U1 through Un and a matrix B with respect to a basis V1 through Vn. Then let S be the change of basis map from, so we're going to call this U, we'll call this V, from U to V, then in terms of coordinate vectors, the following diagram commutes. So we have the map from R2, or I'm sorry, Rn to Rn. With respect to the basis U, and this is given by the matrix A, and then we have it in terms of the basis V, and it's given by a matrix B, and we also have our change of basis map. And so we have a map S that goes from the coordinate vectors with respect to the U basis to coordinate vectors with respect to the V basis. And so we obtain this diagram. Thus, B may always be expressed as follows. S times A times S inverse, where this is basically the matrix computation. So if you think about how this works, what it's essentially telling you is that if you know this matrix and you know this matrix, then you can figure out the matrix B by going the reverse direction here, and then over by A, and then down by S. S inverse, A, S. You're doing kind of an N shape, or a reverse U. And by doing that, you can compute the matrix B in terms of the matrices for A and the matrices for S. So this is how you change bases for a linear transformation. Let's give a definition to this idea. So suppose you have two n by n matrices, A and B. Then B is said to be similar to A if there exists a non-singular matrix S such that B is equal to S inverse times A times S. So here you'll note that the inverse is on the left side rather than the right, but it doesn't really matter. Because you could just as easily replace S with S inverse, so the inverse ordering doesn't matter. What does matter is this relation. This is the fundamental similarity relation, and it's going to be the basis of a lot of computations we do going forward. So now that I've introduced kind of the formal notion, I want to turn to some examples to kind of give you a feel for how this works. So here's our first problem. So let D be the differentiation operator on P3. And here, let me remind you guys that P3 is polynomials of degree less than 3. And what I want to do is I want to find the matrix B representing D with respect to this basis, and the matrix A representing D with respect to this matrix, or this basis. So let's do it. I'm going to call this basis here U, and I'm going to call this basis here V. So the first thing I'm going to do is I'm going to find the matrix B with respect to the basis U. So what I can do is I can note that P3, or sorry, I should use a subscript here. So P3 here can be understood as basically polynomials ax squared plus bx plus c, where a, b, c are real numbers. But I can identify this with R3, which is just the set of vectors, column vectors with 3 components. And you can clearly see what the identification is. So if I'm using this basis for P3, what I'm really doing is I'm thinking in terms of these coordinate vectors. So if I take a polynomial like this, ax squared plus bx plus c, and I apply the differentiation operator, well, this will give me 2ax plus b, and the constant term goes to 0. So what happens to the coordinate vectors is that the coordinate vector a, b, c is mapped to the coordinate vector 0, 2a, and b. Well, I can understand this as this is a linear transformation, so I can write down its matrix. And it's pretty easy to eyeball it. This right here is the same thing as 0, 0, 0, 2, 0, 0, 0, 1, 0, multiplied through by A, B, C. So this right here is the matrix representing this linear transformation with respect to the basis U. So here's what I have. I have R3, U, and I've represented the differentiation operator with respect to the basis U, and it's given by the matrix 0, 0, 2, 0, 0, 0, 1, 0. Now I want to find its representation with respect to the V basis. So if we go down here, we have RV, RV, and we have some unknown matrix B that we want to find. So the first thing I should do if I want to find this matrix B is I should figure out how I change from the U basis to the V basis in terms of coordinate vectors. So I want to find this transformation S. Well, in order to do that, I'm going to go through the same process that I usually do, which is I'm going to re-express my basis U in terms of my basis V. Here's what I observe. 1 is equal to 1 times 1 plus 0 times 2x plus 0 times 4x squared minus 2. And then x is equal to 0 times 1 plus 1/2 times 2x plus 0 times 4x squared minus 2. And then x squared is going to be equal to 1/2 times 1 plus 0 times 2x plus 1/4 times 4. Actually, hold on. Let me give myself a little more space. This shows me that S inverse here times the vector, in this case 1, 0, 0. So this is a coordinate vector down here, is equal to 1, 0, 0. It also tells me that if I apply S inverse to the vector 0, 1/2, 0, I get the vector 0, 1, 0. And if I apply S inverse to the vector 1/2, 0, 1/4, I get the vector 0, 0, 1. So I actually wrote down S inverse rather than S, but that's not a problem because the calculation that we need to do involves both computing S and S inverse. So what I now need to do is I need to invert this so that I can have S as well as S inverse. So first, let's understand what this tells us about S inverse. Well, if we multiply both sides of this by S, we see that S is going to be the matrix 1, 0, 0, 0, 1/2, and 0, and then 1/2, 0, 1/4. So we have S. S was easy. S inverse. How do we do that? Well, we just invert this matrix. So let's go down here and do that computation. So I have the matrix 1, 0, 0, 0, 1/2, 0, 1/2, 0, 1/4, and I want to invert it. So I write down the augmented matrix with the identity on the right-hand side, and I do a sequence of row operations. In fact, I only need to do 2 of them. My first operation is going to be multiplying the second row by 2 and the third row by 4. So row 2 is going to be equal to 2 times row 2. Row 3 is going to be equal to 4 times row 3. If I do that, I'm going to get 1, 0, 1/2, 0, 1, 0, 0, 0, 1, 0, 0, 4, 0, 2, 0, 1, 0, 0. And then the final row operation I have to do is I have to cancel out this 1/2. So I set row 1 to be equal to row 1 minus 1/2 row 3. If I do that, I get 1, 1, 1, 0, 0, 0, 0, 0, and 1, 2, 4, and -2 here. Wait, no, I'm sorry. Yeah, no, that's right. And this right here is my final augmented matrix, I and S. Or, I'm sorry, S inverse. So I have figured out S inverse and I have figured out S, and now I have all the data I need to figure out B. So let's take it all. I take this, and I note that S inverse here is going to be 1, 0, -2, 0, 2, 0, 0, 0, 4. I also take my matrix B from all the way back here. Or I'm sorry, this was my matrix A. And now I note the relationship between these three matrices and the matrix B, which is that B is going to be equal to S times A times S inverse. So this is the calculation that we need to do. So to set it up, I take this, I put this over here, I take this, why is that being done? I don't know why that's being done, so instead I'll just circle select it. I multiply that by that, and then finally I multiply by this. So now we have to do a long matrix multiplication computation. So this is going to be the same thing as 1, 0, 0, 0, 1/2, 0, 1/2, 0, 1/4. And then I'm going to multiply these two matrices. So I'll have 0, 2, 0 here, 0, 0, 2 here, and then -4 here, and a 0 and a 0 here. Now I multiply this matrix with this matrix. So let's see what I get. I get 0, 1, 0, and then I multiplied this column with each of these rows. So I get 1, 0, 1/2, and then I multiply this column with each of these rows, and I get -2 and 0, 0 here. And this completes the computation. And it tells me exactly how I can represent my differentiation operator with respect to this basis. Let's do another example. this will be a more straightforward one. So let's suppose I have a linear operator from R3 into R3 defined by the following matrix equation. The matrix A represents L with respect to the standard basis. And now I want to find the matrix representing L with respect to the basis y1, y2, y3. So let's write down our diagram. We have R3, standard basis, R3 with the standard basis. And with respect to the standard basis, it's given by a matrix A. And now we have our y basis. And we want to find the matrix representing it with respect to the y basis. In order to do that, we need to know how to base change. So we need to know how to go from the standard basis to the y basis, etc. What I'm going to do this time is I'm going to reverse it a little bit to make our life slightly easier. And I'm going to worry about, instead, the base change map from the y basis to the standard basis. So again, it doesn't matter which way you do this, but sometimes one way is easier than the other. In this particular problem, it's easier to use the map where you change from the y basis to the standard basis. But it actually doesn't really matter because in both cases you have to compute both this map and its inverse. So let's call this map here S. And let's think about how we change from the y basis to the standard basis. Well, S here is really easy to compute in this case. Going from the y basis to the standard basis is simply a matter of taking these three vectors and putting them into a matrix. So this matrix right here, which is 1, -1, 0, -2, 1, 1, 1, 1, 1. So S is easy, but now I still have to compute S inverse, which is the map going the other direction. And I can do that by, well, essentially just doing a very similar row reduction calculation. I write down the augmented matrix that I'm interested in this case SI, and I'm going to perform a sequence of row operations to it so I can make the left side into the identity matrix. So my first row operation here is going to be to set row 2 equal to row 2 plus row 1. If we do that, we're going to get 1, -2, 1, and then 0, -1, 2, and then 0, 1, 1. And then on the other side of the augment, we're going to have 1, 0, 0, 1, 1, 0, 0, 0, 1. The next thing I'm going to do is I'm going to set, how about I add row 3, or how about I add row 2 to row 3. So I'm going to set row 3 equal to row 3 plus row 2. In which case I'm going to get 1, -2, 1, 0, -1, 2, and then 0, 0, 3, And then the other side of the augment, I'm going to have 1, 0, 0, 1, 1, 0, 1, 1, 1. And now I do a bit of work. I take this to a new slide. So the first thing I'm going to do here is I'm going to divide the second row by 3. Do I really want to do that? Actually, I'm going to do something else. I am going to set row 1 equal to row 1 minus 2 times row 2. If I do that, I'm going to get 1, 0, and then negative 3, and then 0, negative 1, 2, 0, 0, 3, 1, 1, 0, 1, 1, 1, and then here I'm going to have negative 1, negative 2. I'm also going to divide, actually, to change this a little bit, I'm going to set row 3 here to be equal to 1/3 row 3. This is 1, this is 1/3, this is 1/3, this is 1/3. Next thing I'm going to do is I'm going to set row 2 to be equal to row 2 minus 2 row 3, and then row 1 will be equal to row 1 minus or actually plus 3 times row 3. And this is the calculation that we need to do. So I'm going to have 1, negative 1, 1, 0, 0, 0, 0, 0, 0 on the left, and on the right, well, I'm still going to have 1/3 all along the bottom row. Going up, I'm going to have a negative 2/3 here. I'm going to have a 1/3 here, a 1/3 here. And then I'm going to have a positive 1 here, a negative 1 here, and a 0 here. And so the final thing I have to do is I have to set row 2 to be equal to negative row 2. In which case I'm going to get the identity on the left. And on the right, I'm going to get 0, negative 1, 1, negative 1/3, negative 1/3, 2/3, and then 1/3, 1/3, 1/3. Okay. And this gives me S inverse. Now I can take all the data I have and I can assemble it. So I have this diagram to begin with. So I'm going to take that, move it to a new slide. I'm going to take what I know about S and A. So I know my S, which is this. I also now know my S inverse, namely this. And the next thing I need to do is get my A as well. So A is from here, so let me transcribe it. A is 2, 1, 1, 2, 1, 1, 0, 2, 2. So I have A, I have S, I have S inverse, and now what I really want to do is I want to figure out what B is. So to understand B, let's think of the diagram we have. This diagram commutes. So what I can do is I can apply S to go up to change basis to the standard basis. And now that I've changed basis to the standard basis, I can go over by A. And then I can go down along S inverse. And so this would tell me that B here is the same thing as S inverse times A times S. Because again, when you're looking at this equation, you should imagine it going from right to left. S is the first thing we do, A is the second thing we do, and S inverse is the third thing we do. So now we have to do a long, tedious computation. So we take the matrix A here, and then we multiply it with the things we just computed. And if we do that, well, what we're going to get here, I'm going to leave this matrix alone for the time being and multiply the other two. So if I multiply this column by this row, I get 0. This column by this row, I get 0. This column by this row, I get 0. This times this, I get, what do I get? I get -2. And then here I'm going to get 1. Here I'm going to get 1. And then here I get 4. Here I get 4. And here I get 4. Now if I multiply this with this, let's see what happens. I'm going to get 0, 0, 0 here, 0 here, 0 here, here I'm going to get 2/3 plus 2/3 plus -1/3, so I'm just going to get 1. And then down here, I'm going to get 0. If I multiply this by this, I'm going to get 0 here. And then finally, down here, I'm going to get 4. So, having done this computation, I have computed what my matrix B should be. B is just the matrix with entries 0, 0, 0, 0, 1, 0, 0, 4. So, you'll note something about this specific example. By changing from the basis y, or by changing from the standard basis to the basis y, I have produced a matrix that is much simpler. It's very easy to understand how this matrix works, this matrix B. We can see it geometrically. B sends y1 to 0, sends y2 to itself, and scales y3 by 4. So in some sense, the basis y is a better basis than the standard basis for this particular linear transformation. It makes the linear transformation look nicer. And a lot of the computations that we're going to do in the second half of the semester basically involves trying to take a given linear transformation and find a different basis so that when you look at the matrix in the different bases, it is nicer. And this kind of matrix right here, where everything off the diagonal is 0, is basically the nicest that a matrix can be. And we will explore this notion more in the next few weeks. So that's all I have for you today. And I will see you guys Wednesday. And office hours are starting now.